Again, our topic here is one-dimensional projectile motion, which is also called freefall. Now, technically, I think that freefall refers to a situation where the only force on an object is gravity. So we're going to be dealing with one-dimensional motion where the only force on the object is gravity. Now, of course, in real life, a projectile also feels some air resistance. That's a little bit more advanced topic that we're not going to cover in these series videos, at least not right now. Instead, we're going to be focusing on the simple case of projectile motion, which is when gravity is the only significant force on the object. In many cases, air resistance is a somewhat negligible force. So in many cases, it's a good approximation to ignore air resistance. So that's what we're going to be doing, ignoring air resistance and just focusing on the effect of gravity. That is specifically what people mean when they say free fall. Free fall is when you can just focus on the effect of gravity and ignore any other forces like air resistance. So we'll be focusing on one-dimensional free fall and projectile motion. Something that I encouraged you to do in the earlier series of videos on general one-dimensional motion was, for each problem, write down the 5 kinematics variables. So let's try writing down our 5 kinematics variables for projectile motion. Now, we're going to be focusing here on vertical projectile motion. That's the, when you're thinking about one-dimensional projectile motion, what you're thinking about is vertical projectile motion. So we're going to be imagining experiments where, for example, an object is thrown up and then eventually falls back down. Or maybe experiments where the object is just dropped and goes down or is thrown down. So we're only going to be focusing here on vertical motion. In this series of videos, we're only going to be focusing on vertical motion. We're not going to focus on projectiles that are also moving horizontally, because that would involve 2 dimensions. Well, that's certainly very interesting, but we're not ready for that yet. Before we can get to 2 dimensions, we should just focus on one-dimensional vertical projectile motion. Okay, so in these videos, we're focusing on vertical motion. So it would make sense then to, instead of using an x-axis, to use a y-axis, because typically people use a y-axis to indicate vertical. Usually we use the y-axis for the vertical and the x-axis for the horizontal. So in this series of videos, we're pretty much always going to be thinking in terms of a y-axis, not an x-axis. So what are the kinematics variables going to be? Try writing down the 5 kinematics variables. In these videos, I'm going to be posing a lot of problems and questions to you, and I hope that after every single problem or question, you will pause the video and try writing down an answer on your own before you proceed. You're going to get a lot more out of the videos if you do that. So I hope that you've tried writing down the 5 kinematics variables for vertical projectile motion. Here's the 5 variables for vertical projectile motion. Notice that we're focusing on y components. Like I said, for vertical motion, it makes sense to use a y-axis, not an x-axis. So we have delta y for the vertical displacement, v initial y and v final y for the vertical velocities, a sub y for the vertical acceleration, and then t for time. So those are going to be our 5 variables. Now, one of these variables we know automatically when we're working with vertical projectile motion. Which of these do we know automatically? By the way, I'm expecting that it's likely that most of the people who are watching these videos are not trying to learn the material from scratch. Probably most of you watching these videos have already tried to learn the material from your textbook or from your course, and you feel like you need some extra help. So if you've already seen this material before, you should already have some idea of which of these we already know. Well, we kind of already know the vertical acceleration. Now, it turns out that accelerations come from forces. You're going to learn about that pretty soon in your physics course when you're studying Newton's laws. You'll see that accelerations come from forces. Accelerations come from forces. Well, remember that we're imagining that the only significant force here is gravity. For our vertical projectile motion, we're going to ignore air resistance. The only significant force is going to be gravity. And that means the only acceleration we need to worry about is the acceleration from gravity. We're just going to be focusing on the acceleration from gravity. Well, what is the acceleration from gravity? You might have already encountered the number that the acceleration from gravity is 9.8 meters per second squared. The acceleration due to gravity is a constant 9.8 meters per second squared. The force of gravity is constant on the projectile, so the acceleration from gravity is also going to be constant. Remember that if the acceleration wasn't constant, we couldn't use our normal kinematics approach anyway. Remember that all of our kinematics equations are based on the idea of a constant acceleration. Well, we have a constant gravitational acceleration, so we can use our kinematics approach. So it turns out that numerically the acceleration in standard units from gravity is 9.8 meters per second squared. So every single problem that we do in this series of videos, we're going to start out with an advantage. The advantage is that we know right off the bat what the vertical acceleration is going to be. Since it's coming from gravity, we know that it's going to be 9.8 meters per second squared. If you watched my earlier series of videos, you should be getting kind of uncomfortable. You should be uncomfortable because I haven't indicated a sign in front of this acceleration. And I've been emphasizing how important it is to always put a sign, not just in front of negative numbers, but also in front of positive numbers. So should this be positive or negative? That was actually a trick question. Until we choose our positive direction, we don't know whether this should be positive or negative. If we choose up to be our positive direction, then this should be negative because gravity is pulling you down. Of course, gravity is pulling you down, so if up is the positive direction, then gravity would make you accelerate in the negative direction, which is down. But sometimes it might be more convenient to choose down as the positive direction. If we choose down as the positive direction, well then this acceleration would be positive because it's going down. So the safest thing to say right now, since we're just trying to talk about these problems in general without choosing an axis, the safest thing is just to say that this is 9.8 meters per second squared down. It's definitely down. We don't really know whether it's positive or negative until we've chosen a positive direction. So all we can say right now is that the acceleration is 9.8 meters per second squared down. And when we choose a positive direction, then we can put the sign in front to show whether this would be positive or negative. So the magnitude of the acceleration due to gravity is 9.8 meters per second squared, and the direction of that acceleration is always down. That should be kind of common sense. We know that gravity makes things accelerate down. Gravity pulls things down. By the way, we just said that the acceleration is always going to be down in these problems. Does that mean the object is always moving down? Since the acceleration is always down, does that mean that the projectile can only move down? Well, no, of course not. As you saw in the earlier series of videos, the acceleration does not tell you which way you're moving. The acceleration does not tell you which way you're moving. Just because the acceleration is down doesn't mean that you're moving down. Remember, it's the velocity's job to tell you which way you're moving. So you can be accelerating down but still moving up. That's totally possible. So just because we're always accelerating down doesn't mean that we're moving down. Now, you've probably seen in your textbooks that there's a common symbol for this number. The common symbol is 9.8. The common symbol is G. Textbooks commonly use the symbol G to indicate this constant 9.8 meters per second squared, which is the acceleration due to gravity. So let's make a couple of points about that. First of all, again, let's focus on the signs. So the convention is when your textbook uses the letter G, what they really mean is the magnitude of the acceleration. So if your textbook just uses the letter G, you should assume that this is just standing for the magnitude of the acceleration. So you should never plug in, say, a negative number for G. You should never plug in negative 9.8 for G, because your textbook just by convention is using G to stand for the magnitude of gravity. The only exception to that is if your textbook actually puts a vector arrow on top of it. Well, then G includes both the magnitude and the direction. Or maybe if your textbook wrote the letter G in boldface. I can't put boldface on the board. But if it was in boldface or with a vector arrow, then you would know that they were talking about both the magnitude and the direction of G. But that's pretty rare. Usually in your textbook, you're just going to see the letter G in italics. And the point I want to make is that when you see the letter G in italics, that just stands for the magnitude of the acceleration due to gravity. So you should not plug in a sign when you see the letter G, because that's just standing for the magnitude, and magnitudes are always positive. In my last series of videos, I briefly mentioned that I think it's actually useful to have a separate symbol for when you're referring to a magnitude. I think it's helpful to have a separate symbol for when you're referring to magnitudes so that you don't get that confused with variables that refer to signed numbers. So the symbol that I've invented is a dot. I like to put a dot on top of a variable when it's just representing a magnitude. So if I was writing the textbooks, every time I wrote the letter G, I would put a dot on top of the G to remind people that the letter G just stands for the magnitude of the acceleration due to gravity. Even though your textbook isn't going to do that, you should be mentally putting in that dot. You should be saying to yourself, whenever you see a G in italics, you should be saying, this just stands for the magnitude of the acceleration due to gravity. It doesn't include the sign. That's just the convention for what an italics G stands for.